Today we're going to be looking at Module 7, Lecture Notes 14. We're going to pick up where we left off talking about different models of the atom and how we came to know the model that we do today. Before we get to our notes, I'd like you to take a brief look at this timeline. And I think it does a really good job of putting in your mind a picture of how scientists began looking at the atom. Here, Dalton thought it was just a solid sphere. He didn't know that any subatomic particles existed. Later, scientists like Thomson, using his cathode ray tube experiment, added the electron to our idea of the atom. Then we got the nucleus from Rutherford's gold foil experiment, and I'm sure you read about that in your book as well. So you can see how the atom is evolving into the picture we know today. Today in our notes, we're going to talk about these later two models of the atom, the Bohr model, and then finally the quantum mechanical model, which is also sometimes called the electron cloud model. And you can see why. It looks like there's a cloud of electrons around the nucleus. So hopefully that gives you a visual for how the discovery of the atom has evolved through time. Okay, so let's grab your notes paper and look at these latest two models of the atom. This model here was discovered by Niels Bohr, and it is often referred to as the planetary model. And I think you can see why. Here's our nucleus, and the electrons are orbiting the nucleus, a lot like the planets orbit the sun. So it got nicknamed the planetary model. And what Bohr said was that when elements were heated or electrified, they emitted unique sets of wavelengths. So he thought that electrons resided in very specific energy levels. And that's why he drew his model to look like this, with different energy levels coming out from the nucleus. He said that electrons can jump up to a higher energy level when they got excited. And I think you did that in your lab last week when you excited electrons in your lifesaver or in your Band-Aid wrapper. Okay, so we can say that an electron will gain energy when it becomes excited, and it will jump up to the next energy level. Well, electrons aren't going to stay at that higher energy forever. They're eventually going to fall back down or lose energy. Okay, and when they do that, when they fall back from a higher energy level to a lower energy level, light is emitted, and that's what you see. Adding on to this model of our atom, Erwin Schrödinger said that electrons probably don't reside in these fixed energy levels, but more likely that they reside in a cloud of probability around the nucleus. And that's where we get the term electron cloud. Okay, so the electrons are moving around the nucleus in a cloud of probability. They're moving quickly, and if you were to think of it like a windmill, the electrons are moving so fast that you cannot pinpoint the exact location of an electron in the electron cloud. But we know that they're there because it's negatively charged. These clouds of probability we call orbitals. And we say that the electrons reside within these orbitals. There are four kinds of orbitals: S, P, D, and F. In this class, we're going to focus on S, P, and D. We may talk about the F orbitals, but they will not be the focus of our in-class lectures. S orbitals, there's only one type. They are spherical. P orbitals are shaped like dumbbells. And you can see that there are three types or three different orientations that you could have this dumbbell. You could have it running up and down on the y-axis, you could have it horizontal on the x-axis, or you could even have it on the diagonal. So there are three different shapes for the p orbitals. And the d orbitals, their shape is just called complex. and there are 5 shapes or 5 types. Now, each one of these orbitals can hold 2 electrons. This is very important. Okay, so the way that we draw or notate an orbital is we draw a line, and we show the electrons residing in that orbital by these little lines. I always draw one up and one down, because notice it said that each orbital can hold 2 electrons with opposite spin. So one will spin up, one will spin down. A s orbital can hold a maximum of 2 electrons. For our p orbitals, since we have 3 different types, p orbitals are denoted by 3 lines. If I fill these orbitals with electrons, remember each can hold 2, the p orbitals would hold a maximum of 6 electrons. How do you think this pattern would finish for the d orbitals? I would draw 5 lines for each one of my types, and I would be able to hold 10 electrons. Okay. When I was writing those, notice that I always fill each orbital with 1 electron first, then I go back and finish them with the rest. Okay. The last rule that we need to talk about is this one. Electrons will always fill the lowest energy orbitals first. So electrons are going to fill our s orbitals. When the s orbital is full, we will move on to p, and when the p orbitals are full, we will move on to d. So these are kind of the baseline rules for putting electrons in orbitals. So what does this have to do with the periodic table? Well, if you're someone like me who likes organization, this is going to blow your mind. This works out perfectly with the periodic table. We said that s orbitals can hold 2 electrons. I want you to outline these first 2 columns on the periodic table. And over here, make sure you get helium. It also technically is part of the s orbitals. Notice how these 2 columns are 2 columns wide. These are going to be our s orbitals, 2 electrons. If we go on to p, we said 6 electrons can fit in the p orbitals. Well, this block over here, 1, 2, 3, 4, 5, 6, magically works out that it is 6 elements wide. These are going to be our p orbitals. Label those your p orbitals. And then, of course, it works out that our d orbitals can hold 10 total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This block here in the center of our transition metals is 10 elements wide, and these are going to be our d orbitals. Don't you just love patterns? Okay, so once you have that labeled, you can stop there and flip your paper over, and we will talk about how to do some practice problems with these. Okay, so why do we care about electrons and orbitals and electron configurations? The electron configuration is like the address of an electron. It tells us with the highest probability where an electron is going to be located around an atom at any given time. What orbital is it going to be in? What energy level away from the nucleus is it going to be in? Okay, so each element on the periodic table has an address for the electrons within its atom. So let's just jump into an example. We're going to start really easy with hydrogen. And I want to write the electron configuration. Well, hydrogen only has 1 electron. So its electron configuration is going to be 1s1. I put the energy level, which is the row, 1. I'm in the S block, and I have 1 electron, 1s1. Let's go to lithium. Lithium is down here. Whenever you do these, you must start at the very top of your periodic table, and you're going to read this across like you would read a book. Okay? For lithium, I would say 1s2. I have to fill this whole first row, and there's 2 elements I must pass through. 1s2. I filled the first energy level, 2 elements. Now I go down here to 2s1. I'm the first electron, or the first element, in the second energy level, 2s1. For those of you who like to check your answers, like I do, you can always add these superscripts. 2 plus 1 is 3. Make sure it matches how many electrons you should have in your element. Lithium is element 3, so I know that I wrote that configuration correctly. Okay, let's go a little bit further. I want to do carbon. I always find my element first so I know where I'm going. Let's start back at the top. 1s2. 2s2. I have to fill both of these s rows. And remember, an s orbital can only hold 2, so I can never have a number greater than 2 with s. These two columns are full. Now I jump over here, and I'm in a p block. Okay, I'm in row 2. I'm p, and I'm the second element over, so I say p2. Okay, these will start to have a rhythm to them that you can feel. Let's start back at the top and get to carbon. 1s2, 2s2, 2p2, and I count to the second one over, and that's how I get my electron configuration. 2, 4, 6. Make sure my superscripts add up to my element, and I'm good. I want you to try phosphorus on your own and see how far you can get, and then come back here and check your answer. Okay, I always like to know where I'm going. We're going to phosphorus, and let's try to say these together. You can even say them out loud as you're probably writing this in your room by yourself. I think this really helps you get the rhythm in your mind. All right, start back at the top. 1s2, 2s2, 2p, I go all the way through, 2p6, 3s2, 3p, 1, 2, 3. Yours should end in 3p3. So here's the whole thing again. 1s2, 2s2, 2p6, 3s2, 3p3. You can make sure these add up to 15. They should. And you've done phosphorus. Okay, before we look at the last 2 examples in that section, we're going to talk about this extra sheet that you should have along in your notes. So I like this version because it can help you see things a little bit bigger. You can practice filling 1s2, 2s2, 2p6. But I want you to notice what happens when you get here to the D block. Okay? These energy levels, 1, 2, 3, 4, 5, 6, 7, followed right along with the number of rows on our periodic table. But when we get here to the D block, notice that the D block, the energy levels are 1 lower. And that's just something you need to note and you need to watch out for when you are writing your electron configurations. So you might just want to write D block is 1 energy level lower. All right, so let's go back and let's apply that to our next example for silver. If it also helps you remember, you can write in here that this is going to be 3D, 4D, 5D, and 6D when you get to filling those orbitals. All right, so we're going to do silver. Silver is the element Ag. You can put a little dot on it. It's right here. Okay, we're going to start at the top together with our rhythm. We have 1s2, 2s2, 2p, how many is a p? 6. Now I'm here. I say 3s2 to get through these two columns. 3p6, I fill all the way to the end. Now I'm down here at 4. I'm going to fill the 4s, 4s2. And then I come to 3D. Right after element 20, I go here to 21. And I'm going to fill all the way through 3D. There's 10 of them. 3D 10. Now I'm back at P. And remember, P follows the energy level rule. So this would be 4p6, 5s2, and then I go to 4D, and silver is somewhere within this D block. So I don't want to go all the way to 10. I'm going to be 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to end with 4D9. Okay, if you want to do a quick add of all these superscripts, they should add up to 47 for my element silver. I'd like you to take a second to try to get to strontium. Strontium is Sr, and where did it go? Well, oh, here it is. You're going to try to get to strontium, and then we will check it together. Okay, strontium Sr, we're trying to get right here. We're going to do these together in our rhythm. We're going to start at the top. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then I stop. I have it written out for you here so you can check to make sure you have your energy levels correct. A big one to check is make sure you got the 3D, 4s2, 3d10, 4p6, 5s2. If you want more practice with electron configurations, I think the best thing that you can do is just randomly pick an element. Put your finger on it, put a sticky note on it, put a dot on it, and just try to get yourself from the top all the way down to where you put your dot, and then check your answer. I think that's the best way to really practice this rhythm and get it ingrained in your mind. Okay, well, these can get kind of lengthy, and once you get the rhythm down, it can get very, very repetitive. So, luckily there is an abbreviated electron configuration, which means that you can write it shorthand. For this class, if it says write the electron configuration or the full electron configuration, your teachers probably expect you to write the full thing out. If they've said you may use the abbreviated form, then this is what you can do. This is also called the noble gas notation. Remember, our noble gases are right here in this last column. So what you can do is you can write the last or the previous noble gas that comes right before your element. So if we do this first one together, and we're looking at strontium, which we just did, it's element 38. So you're going to back up to element 37, element 36. Krypton is the noble gas that comes right before strontium. You're going to put it in brackets, and you're going to say krypton right here, and then just 5s2, because that is the noble gas plus the finish of the address for your electron configuration. You're basically cutting all of this off and then just putting the last part. Okay, and in reality, if somebody told you 5s2, you would be able to count down 1, 2, 3, 4, 5 rows, the S block, 2 over, and you would know they're talking about strontium. So it is still a very accurate address for your element. I would like you to try these last two and then come back and check them. So selenium is element 34. The noble gas that comes right before it is actually up in the previous row. It's argon. So you're going to say argon, 4s2, 3d10, 4p, 1, 2, 3, 4, 4p4. Iodine, same thing. Find your element. Go to the noble gas prior to it, which would be krypton. So you have krypton, 5s2, 4d10, 5p5. Now, how can you check your answer like we were doing with these shorthand notations? Krypton is element 36, so it has 36 electrons, plus 2 more, plus 10 more, plus 5 more, and you still should end up with 53 electrons, and you can check your answer and make sure that matches iodine.